So can we or can we not? We'll figure it out in a few minutes. With that, Professor KV, over to you.
Thanks, Vinay. Thanks for the very generous introduction. Yeah. And thanks to Ram TP Foundation for giving me this opportunity. Yeah. I will straight jump into the talk. So this is going to be a sort of what I would call it is really an outreach talk, as Vinay mentions. The idea is to sort of give you a flavor of the kind of computer science that you would see if you were to become a theoretical computer scientist. Of course, theoretical computer science has its impact on practical computer science also. So I hope to sort of convey to you the excitement of doing theoretical computer science. Of course, all kinds of computer science is exciting, I think. Yeah. Okay. So what I will do is I will take you through this. If there are any questions, you may write it in the chat, or and then Vinay will point it out to me. That's what we've decided. Yeah. Okay. So I'll start right away. Okay. Let me start this presentation. Yeah. So this is, so did anyone try? So as you see, even the number that I gave you does not fit. Clearly, the number that is currently there on the slide, that is clearly factorizable. You can pull out 100 from it for sure. And then you can even pull out a 3, perhaps. You can pull out a 3. You can pull out a good number from the end. So the number that I gave you, of course, didn't end with 0, 0. It ended with something which was a prime number. Yeah. But this is the question that we would like to address. I mean, what is it to factorize? And what do I mean by, can you factorize it for me? Can you? So let us see what I mean by this. Okay. So you are all probably aware that even as children, many of us, in fact, I'm sure most of you also would have seen this rather nice frame which children play with. So there is a frame which has a number of shapes on it, and a child has to take a block and try to push it into that frame. There are different, if you want, there are different kinds of shapes. One is a triangular, one is a sort of square, and there is a star somewhere here, and so on. So this is what the child has to do, and one learns over time how to do these things. Yeah. Okay. Now let us see. So then there are other kinds of puzzles also you probably solved. I mean, as you grow older, you get into slightly more complicated puzzles. So here a child is actually probably making a map. So there is a jigsaw puzzle. There is a bunch of pieces, and you need to fit the pieces to construct some object that is there on the cover of the box that you see. So these are sort of problems that are interesting. Okay. So so suppose I ask you, can you describe what the child in the first picture was doing? What would you say? Can somebody, I mean, I just want you to sort of tell me what you think the child was doing so that we can write it down. Can somebody unmute and then tell me?
So we can say that the child was trying to explore with the shapes of each of those objects and trying to fit in and see if that outline was matching.
Okay. Okay. The child was, 1 minute.
Matching one shape to another,
Matching one shape to the other. The first one was about, okay. Yeah. Sorry. Let me use this perhaps. Yeah. Yeah. Explore. This is visible. The
Yes, yes, very much.
outlines on the block with the outlines on the frame. So that is correct. And then try one by one. The outline on the frame. So you have a block in your hand, you try one by one and try to push it in. Is that okay? Are these activities, does this describe what the activity of the child is? Does anybody have anything else to add to this?
Saket,
Yeah, somebody
uh,
said something.
can can Saket add on?
Yes.
So,
Yeah, please do
in
so.
both the activities, you have to the
Yeah,
child is trying which possibility will work.
yeah, try to see which possibility works. So as in, I cannot fit a circle to a triangular shape. Yeah. So if the child has something which has a circle, he cannot fit it into a triangle. Correct? That's what you mean, right? Yes. Okay.
Yes.
He
Yes.
says
Yes.
yes. Okay, good. Yeah. So clearly, this is a way to describe the activity of the child. Yes, clearly. So let us now see uh, uh, whether I can sort of understand this. So the child is clearly trying to compute something. And it is useful to think of this a bit abstractly. So what does it mean to compute? The child is, oh, I should go to presentation perhaps. Yeah, okay. So let me try and whatever you've said, let us try and write it in a language which is slightly more precise. That's all we will do. Okay. So what is the input? The input is what the child has in her hands, which is a frame. That frame has various 2D shapes. So there is so these are all 2D shapes, correct? There is a triangle on the top, there is a circle on the top, there is a star, and so on. And the child is really looking at these. So that is what the child has in her hand, and there are holes marked on it. And then there are pieces whose boundaries really match some of the shapes that the frame has. And the pieces that the child has in her hand are pieces which are outside the frame, correct? They're outside the frame. And what is the child's job? The child's job is to finally finish when the puzzle finishes, you want all the outside pieces to be inside. Is that okay? Does that make sense? Do you agree that if this is what the child is starting with, then in the end, after the child has finished the puzzle, this is what you would see as output? That all the pieces that are outside will go in. Yes, somebody agrees with me. Yes, indeed, that is. So one can think of what the child is doing as taking this input, which consists of the frame with various 2D shaped holes on the outside, and a bunch of pieces which are also outside. And from that, the child has to come back and produce something for you. And the child is following a sequence of steps. What are the steps that the child is following? So long as there is some piece which is still outside, what does the child have to do? Pick up that piece and hold it in her hands, and then the child will see the shape that is there on the top of that, correct? And then the child will try and push the piece into the hole that he sees, that she sees rather. Yeah. If this shape does not fit into the hole, the child will move to the next hole. That is a reasonable thing. Yeah. And then what happens after this? Finally, the child finds that she can push some shape into it. And if there is no other piece left, the puzzle is solved. So the output is obtained. The child will clap hands and finish. It is done. Otherwise, if the child there are still some pieces which are outside, then the child will go back here and once again start the whole process. Yeah, till this whole thing is over. This is what the child is going to do. The child is going to pick up a piece, look at it, look at the hole, as somebody said rightly, is trying to match. Yeah, and then try to push the piece inside. This is what the child is doing. Completely right. So now, what is true? That this kind of sort of process that the child is actually doing. The child is really small. In the first picture, if you notice, the child was really tiny. Yeah, because you can even see the hands. There are small hands. The child was really small, but nevertheless, the child is still able to do some complicated computation. And in fact, if you look at it, it turns out that there is, oh, it's a bit painful. 1 minute, sorry. I have to go back. Okay, I'll start this. Yeah. So anything that the child is doing is some kind that what the child is really doing is doing some kind of sort of sequence of steps in her mind. And that sequence of steps is what I will say is a computation. Yeah. So we'll define this a bit more formally very soon. And if you look at it, it turns out that in nature, there is a lot of computation that actually goes on. For example, in your brain, there are various kinds of circuits that are there, and there are some calculations that are going on all the time. So in fact, even as the child develops, you see, from the embryo to the in the mother's womb, when the child develops, there is a lot of computation that nature does, starting from here to finally produce a child which is sitting like this after about 40 weeks. And then the child is ready to come out into the world. Going from here to here, nature is doing a lot of computation for us so that you can actually go from here to here. Yeah, and a full baby is actually formed, and that baby is now ready to come out to the world. So this is even as even inside the stomach of the mother, there is a lot of work that nature is doing to get from the embryo to the full-grown child inside the mother's womb. Yeah. So there is actually some computation that nature performs for you. So what actually happens in the nature? So it turns out that we understand it. We don't understand it very much. We understand it to some extent. So in our bodies are what are called DNA. So some of you may have seen it in your biology. So DNA is a long sequence. So have most of you heard about DNA, or have some of you heard about it? Yes. So I see a lot of yeses. Is there anyone who does not know what DNA is? Is there somebody who does not know? Oh, very good. Somebody has given me the full form also. Yeah. So it looks like most of you know what it is. Yeah. So what exactly is happening? The DNA actually encodes instructions. Yeah. A sequence of instructions. That is what the job of DNA is. And what does the DNA use it for? Some parts are used to produce a nose. Some parts of the DNA are used to produce an eye. Some parts are used to produce proteins. So there are various instructions that are present in your DNA, which is how the embryo grows into the child. The embryo starts off, then some protein is formed, some protein is produced. There are some instructions to produce the protein. Then from that you get after some point of time, you will see a nose sort of slowly develop in the embryo. Then you will see other things that are you will see an eye, you will see a nose, you will see a mouth, you will see ears. So slowly these instructions are being executed inside the mother's womb till finally and slowly over 9 months, once a full be inside the mother's womb. Yeah, so this is how nature actually is making the child from the embryo. It is executing a sequence of instructions to finally form the baby. So nature is also computing much like what the child is doing. The child also has picked up a piece, looked at it. So those are the instructions the child is somehow following magically in her mind, that I need to hold the piece carefully, I need to look at it, then I need to look at the hole, I need to push this object into the hole, see if it goes. If it does not, then I try the next hole, and so on. And sometimes after a few iterations, the child immediately knows when she picks up a cylinder that the cylinder has a circle on the top. And then she immediately knows that there is a circle somewhere in the frame, and I should just push the cylinder into the frame via the circular hole that I see. So these are things that the child slowly learns as the child plays with the object more and more. Yeah, in much, of course, nature is not. Nature is doing something very similarly, something very similar. So all these are instructions. So you must have seen this picture of the DNA. In fact, this is not only how organisms like human beings process instructions. These kinds of instructions are present in all kinds of organisms, including the coronavirus that we see. There we don't call it DNA, we call it something. We call it RNA. So those viruses that are there, they also have some sequence of instructions. Those instructions are used by the virus to propagate and get into the body of human beings, and then it causes diseases. So much of life is really this. Each organism has in their bodies a bunch of things called DNA and RNA, and these are used by the organism to grow. So either grow themselves or grow in somebody else's body like a virus is growing. So this is something that most of you have probably heard about. Yeah. So what is RNA? Well, RNA is something very similar. I mean, I'm not a biology expert to tell you what RNA is, but viruses, for example, don't have DNA. They only have RNA. But those RNA are able to sort of process and so DNA allows us to replicate cells actually, whereas RNA just has instructions on how to replicate a cell. There are no living cells inside a virus. The virus has to get onto some other organism which actually has cells. Somehow that RNA in the virus has to sort of attach itself to the RNA in the host cell. Then it goes and executes the instructions that are present in the RNA of the virus get executed inside your body, and more viruses get produced that way. So that is what happens in a so the full form of that is ribonucleic acid. Yes, correct. Yeah, but this is, so my whole point is to tell you that every organism sort of learns how to grow or how to grow by processing sequence of instructions which are very similar to what we do when we calculate. Yeah, so these are also, nature also actually is computing. In fact, computation is something that is very common to nature, to what human beings do, what other creatures also do. Even ants are computing, even birds are calculating some things. So when birds travel long distances, so there is some, although much of it is probably encoded in their genes, there is still some calculation that is actually going on. So some computation that is going on. Yeah. So this is the point of what I wanted to say so far. So are you with me? Is everybody with me so far? Are there any questions? Yes. Okay, very good. Okay. Okay. So now if I, what is this? Why is this? This is not working too well. So computational problems. So this was not supposed to be black. So anyway, so what is a computation? A computation is a process of transforming an input to an output. Yeah, so there is an input, like in the case of what the child was doing, there is an input and there is an output. So in the case of DNA, the input are a bunch of proteins, that a bunch of chemicals that are required, and the output is going to be a protein. That is the computation that is happening inside maybe DNA. Yeah. So every computation requires an input and produces an output. So for example, and there I can always think of any computation, therefore, as a function. So it is really taking an input and producing an output for you. Yeah. So in much the same way as these are functions that we are that are very familiar to us. For example, addition of two numbers. I claim an addition of two numbers is also a computational problem. And what is being computed there? What is the input? The input there is, of course, two numbers. And what is the output? The output is if the two numbers, I call them x and y, the output is the value of x plus y. That is what addition does. Addition is also a computation process. So now if you tell me, can you tell me what the input for multiplication is and what the output for multiplication will be? Even spiders have to calculate, yes. Okay, now coming back to this question, what is the input for multiplication and what is the output? Yeah, so okay, very good. Somebody has already given me the answer. Yeah, saying x and y. So you take two integers or two numbers, and from these numbers, you need to produce for me the number which is the product of this. Okay, so now if I, can you think of the following problem as a computation? Is a given number a prime? So what is my input in this case? A positive number, some integer perhaps. Yeah, input in this case are integers. We can assume they are positive. And what is the output? Boolean. What can you tell me what you mean by that? True or false? Yes, the output is true. Very good. If it is an integer, if the input is an integer, is prime, and false otherwise. So clearly, even this problem of testing whether a number is a prime can be thought of as a computational problem. Searching for information on the net. Yeah. So what would be the input for this? Yeah. A question, a string. Let us think of it as a string. For example, I might say Ram TP. Yeah. And what would the output be in this case? Very good. Somebody says topic, the results. So in this case, if you had typed Ram TP, what would you see? You would see a bunch of information related to raising a mathematician training program, correct? Information about Ram TP. That's what you want. But of course, when you type this on Google, you get other information also. So in that sense, but there is some information that you are interested in. In your mind, you knew that when you wanted to type Ram, when you typed Ram TP, you wanted to really get information about raising a mathematician. So that is really also what Google search engine is doing for you, is also a computation, finally. Yeah. So computational problems are there everywhere. Yeah. Everybody deals with computational problems. Yeah. So like somebody said, the input is something that you're looking for and the output is the result. In this case, there are many results that are presented to you by the Google search engine, and one of them hopefully is your answer. Yeah. So exactly. So this is really what is okay. Okay. So now it turns out that this way of thinking of what nature does, or what you and me do when we add numbers as children, when we multiply numbers as children, thinking of this whole thing as a computation that is common across human beings, across nature, across other creatures. This whole way of thinking about what we do when we process this kind of information and transform an input to an output, it was formalized in the early 1930s. Yeah, and there were sort of great mathematicians of those times who actually gave it a very formal definition, and that is my goal today, to try and explain to you what these formal definitions are. So among the founders, one of them was this gentleman whose picture is here, Does anybody know whose name, what is the name of this person? Alan Turing. Very good. Yes, so in fact, it is Alan Turing. Yeah. So Alan Turing sort of was born in the early 1900s. He didn't live, unfortunately, very long, but in his brief lifespan, he did some remarkable work. Yeah. Among the pieces of work that he did, which we are interested in today, is the notion of an algorithm. So he defined something called a Turing machine, and he formalized the notion of what it means to compute. So we will see that in a short while. Yeah. So he also broke the Enigma code, yes, but that is not something that we're going to discuss today. Yeah. Maybe I have to get on to this. Okay, now I am able to do it better. Okay, somehow it's once again this black thing is hiding something that I didn't want to hide, but anyway, it doesn't matter. So what is an algorithm? An algorithm is a step-by-step mechanical procedure which transforms inputs to an output that we're interested in. And the important thing is also that it transforms it using something called local operations. Yeah. So what is an algorithm? An algorithm is a step-by-step mechanical procedure. It is going to take your input, then do some local operations. We'll see what local, that is very important here. Actually, we'll see what local operations mean. And then from those inputs, you're going to get to an output. Yeah. So it's a set of instructions. But what are those set of instructions? Those set of instructions are instructions that you will perform in order to transform the input to an output. Correct. Exactly. Yeah. So what are the other requirements of an algorithm? An algorithm must work on every input, and an algorithm must take a finite amount of time. That is reasonable. Yeah. So you want to transform the input to the output, but you want to sort of use the same procedure for different types of for inputs of that same kind. So we'll see what it means. So for example, when I add two 10-digit numbers, or I add two 100-digit numbers, are we performing anything different? No. The sequence of steps that we follow is very similar. It does not matter whether you give me a 10-digit number or a 20-digit number or a 30-digit number. The sequence of steps that we follow are very similar. Okay, somebody is asking me a question. Sir, can every process, sorry, I can't read your full question. Can every process?
Let me read it out. Can every process with series of steps have some computation?
Can every process with a series of steps? Well, if those series of steps are sort of are using what has been sort of what has been produced in the past to produce new things, yes, we would call that a computation. Definitely, we would call that also a computation. Yeah, it has, but those series of steps have to be a certain kinds of instructions. So always think of it as transforming an input to an output. Now, when I say inputs, in this case, in the case of numbers, it is very simple, very easy. These are going to be maybe numbers, maybe rational numbers, maybe integers, maybe irrational, whatever. But you fix your numbers if you are talking of integers. Yeah, and then it is taking these integers and producing you something as an output. Yeah, but what we would want for something to be an algorithm is that the algorithm should not depend upon what integers you give me. The output should depend upon that, of course, but the sequence of steps that you are following in some sense should be independent of what actual input you are giving me. Just like when we're adding numbers, yeah, at this point, when you are very young, yes, teachers will only give you addition of 1-digit numbers because they want to teach you that slowly. Then when you go to 3rd standard, they will tell you how to add 2-digit numbers. So at this point, I suppose, can all of you add 20-digit numbers? Can all of you add? Yes. So are you, if somebody now gives you a 30-digit number, are you going to tell that person, no, I cannot add 30-digit numbers? No. Why is it you will tell that person, I cannot add? Why is it you can add 30-digit numbers? From memory? No, not really. Because it is the same process. Exactly. That is the point. That whether you give me 20 digits or you give me 30 digits, the sequence of steps that I need to perform is in some sense very similar. Yeah. It is in fact the same in this case. We know the steps exactly. That is the point of this whole thing. I'm glad you've got it. Yeah. So these were the pioneers. I'll give
Excuse
you
me,
some
sir.
more names, and it'll be nice if you could tell me who these names are.
Excuse me, sir. Am I
Somebody
audible?
has a question?
Yeah, sir, I
Yeah.
had a
Yes,
question.
I can hear you.
In
Yeah.
the definition of an algorithm, you have told
Mm,
us that it has to be finite. Why can I not
mm,
just set a algorithm to, let's say, I take your number, add 1 to the number, and repeat,
mm.
and keep repeating
Okay.
forever? Why can I not just ask it to go into infinity? Whether or not it is useful or whatever,
Yes.
why can I not call my thing an algorithm? And whether or not it's useful, that will break the
No. So
definition
for
of it.
no. So no, no. I have just called it an algorithm because I want to take an input and produce an output for you. Yeah. If you take an input and produce an output after infinite amount of time, for me that is useless. Yeah.
Oh, so you
So I am
cannot get
thinking
an
of
output.
yes, I'm thinking of something which trans. So an algorithm is something for me. It is something which takes an input and produces an output. It is there is a in some sense a before and an after. Yeah. So for me, that is the way I'm viewing it, and because that is the way it really happens also in nature. Nature also takes certain kinds of chemicals, does something with them, executes a sequence of instructions, and at the end produces a protein. Yeah. So
Okay, sir.
this is yeah.
So
Is that
by
okay?
definition, so by definition, that clause which you have put into your definition, it 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 makes sure that you have an input and an output. Without that clause being in your definition, you would not guarantee an output. Hence the importance of
Yeah.
that being that it has to be finite. Because if someone says it's infinite, you're not guaranteeing an output, which is against
Yeah.
what
I'm
an
not.
algorithm
Yes.
is.
So for
Okay,
me, I
thank you,
that
sir.
I
That
that
makes
I
sense.
yes. Yeah. That is the reason. Yeah. Good. Okay. So there were other great pioneers. I mean, there were lots of them, but I will list only a few of them. Does anybody know who this is? Okay, I'll give you some time. This is David Hilbert, one of the sort of fathers of mathematics in some sense. No, Boole I don't have actually. Boole is a great name. I don't have his picture either. But he was another great pioneer. Uh, does anybody know who this is? No, no answers. Okay, somebody called Kurt Gödel. Okay, I forgot the two O's on top, so I should put those two dots also on top. Gödel numbers, yes. He was the one after whom we name Gödel numbers. Does anybody know who this is? No. So this is another great mathematician, logician of that time, actually, Alonzo Church. Yeah. And the last one. So these are, in some sense, my favorite four. I mean, you can have your actually Boole I should have put because he's another great thinker of those times, actually. And does anybody know who this is? No. This is von Neumann. Yes, John von Neumann. Somebody actually mentioned it. Correct. Yes. So these are the people who are in some sense responsible for what we see today. Okay, so once again, coming back to what a computation is, a computational process takes an input and produces for us a desired output. And we do it one step at a time. Yeah, steps are performed in some order. Just like when we add numbers, we do it in a certain order. Example is addition. Of course, all of you know what it means to add. So how does one add? One typically starts by writing the numbers and then starting from the rightmost digit, we will start, correct? We'll start from here. Then you first add these two, you write 9 plus 7, 16, 6 carry 1. Then you'll add whatever is there here and do it. So this is something that you're all familiar with. Yeah. Okay. Then, but of course, if you were Calvin or Hobbes, you would see something completely different. So I don't know if you can read this. Can you read this? Or no, this is a bit too big to read. So here Calvin is asking Hobbes how to add 6 plus 3. And Hobbes gives him some very complicated way of adding 6 plus 3. He says, well, you have to draw a square. In that square, you should put 6. Then you should put 3 somewhere else. Then you should measure the diagonal and so on. So this is Hobbes' way of calculating 6 plus 3. Yeah? He thinks 6 plus 3 is whatever this is. Yeah. But for us, addition means really this. And this is something all of us will agree. Yeah. For us, this is what it is. For tigers, perhaps it is something different. Yeah? Which is okay. Yeah. We can all do whatever we feel is right. Yeah. Okay. So let us write the notion of addition in terms of the sequence of steps that we write. So what do we do? We write the two numbers below each other. Then we start with the units place. For us, the units place is the rightmost place. Then we add the digits in that last column. Then we write the units digit of the answer below the two numbers. If there is a carry, we write it above the numbers in. So we number the columns from left to right, from 1 to k minus 1. And this is something all of you are familiar with. Yeah. And when does one stop? One stops. If the column you're scanning is empty, then you stop. Yeah. So this is the way. This defines for us a good algorithm to add two numbers. Would everybody agree that it fits the definition I gave? Is there something missing? Yes, it does give you the definition, because if you give me two numbers and I arrange it in this nice way on a grid, this way of following steps will certainly give you the answer. No doubt about it. Yeah. Okay. So now, if you've not finished, then you go back. Yeah. Then this is the way you do it. So okay. So now the important question. If I add digits which are this large. Okay. So can somebody tell me before? Let me. I think I have this. We will come back to that statement that ask you this question. Yeah. If I look at this, if you give me the number 10 to the n minus 1, yeah, 10 to the 100 minus 1. Sorry, this is really. Sorry, I'm really struggling with my laptop today. Where are we? I can't see where I am. Okay, this is where we are. Okay, so let me come back to this. Okay, so if I give you this number, which is 10 to the 2 minus 1, what is this number? Can somebody tell me? 99. Very good. If I give you the number 10 to the 10 minus 1, what will this be? How many nines? How many nines do you have? 10 nines. Very good. 9, 9, 9, 9, 9, 5, 6, 7, 8, 9, 10. Okay. Now, if I give you this number, 10 to the 100 minus 1, how many nines will be there? There'll be a sequence of 100 nines. So if this number that you see, 10 to the 100 minus 1, is a really large number. Would you agree? Yes. Do you know how many atoms there are in this world? Do you know how many atoms there are in this world? Millions. Actually, the number of atoms we believe is around 10 to the 80. Yeah. Is this number bigger than 10 to the 80? Yes, this number is bigger. It is much bigger than that. Yeah. But nevertheless, we can add two numbers which are this big. If you give me a number which is this big and another number which is almost that big, I can, yes, I can still add them. Yes or no? If I give you a number which is this big and I give you another number which is this big, we know how to add it. Yeah, how much, let us understand how much time it takes. How many steps will it take for me to add two numbers which are this large? Let us try and see. Then when we are writing it, of course, we are going to use on our notebook, we are going to write. Yeah, and we will keep some little piece of paper to write things as we go along. Yeah, and there we are going to write down 100 digits. How many digits we'll require? We'll require 100 digits. 100 digits. So suppose this is 100. Then what are we going to do? We are going to add this, write it. Then we're going to add this, write it. So that is the way we are doing it. Yeah. So what is important in this is that to represent a number this long, this big, how many digits are required to represent a number which is this big? Sorry, I don't understand what the question is. We require 100 digits to represent it. Correct. So even though the number is very large, I only require 100 digits to write that number. If I give you, if I give you another such number, which is also 100 digits, actually, I know how to calculate this quite easily. I will first add these two, write the answer, then I will add these two, write the answer, carry, add these two. So how many steps am I performing? Around approximately how many steps am I performing? Exactly, we are performing only 100 steps. For this, maybe I will do one step, then I will get a carry, maybe one more step, get a carry, and finally I write down the answer here. So in 100 steps, I have calculated the sum of two numbers which are this large. Do you see that? The numbers are very large, but I can add them very, very fast. Do you agree? Yes. So it is important that the numbers that we wrote down had this very nice representation. Yeah. If I required so many pieces of information to even write down the number, there is no way I could have added those two numbers. Yeah, so it is important that there is a decimal representation. Yeah, it doesn't matter that it is decimal. If it was binary also, we would have been able to do it. Yeah, but it is important that we had some very nice way, very compact way of writing the big numbers. Yeah, simplification of the input. Well, actually, the input is there is a very compact way of writing the input. Yes, so that is the point. Yeah, and this becomes very important when we are talking of computation. Okay, so as I said, to write this, so this was here, I somehow thought it was there. So we take, how many steps do we take? If you actually calculate how much time it takes on a modern machine, yeah. So we had 6 steps for adding. So assuming each of those steps took one quick on a machine. So it turns out that on a modern day machine, to execute one of those 6 instructions that we had on for adding numbers, which is go from right to left, scan what is there, and so on. Each of those operations can be done in 10 to the minus 10 seconds. And as somebody said, we require 100 such sort of steps, and each time we go back. If we find the column is not empty, we go back and do it. So we are executing those Each of those takes about 6 each takes this big. Yeah, and this is really tiny. 6 into 100 into 10 raised to minus 10, hardly 10 raised to minus 8 seconds. In a jiffy you get it. Oh, my voice is breaking, is it? Can others hear? Can you hear me better now?
Yeah, it's
It is
better
fine
now.
Okay, so I don't know, maybe my internet is could be a bit unstable, huh? But I'm glad you tell me this. Yeah, because yeah, so the point is this, that to add these large numbers, I don't take much time. I can do it really, really fast. And this is the point actually. Yeah, that we can add because we know quick, fast ways of adding numbers. Yeah. What about multiplication of numbers? Yeah. What about multiplication of numbers? Multiplication of two numbers. How many steps? So how do we do multiplication? Well, I do multiplication like this, like 5, 2, 1, 7, 4, 2, 6, 5. We multiply the first with this, add, then I get a 3, then I get a 6, then I get a 25, then I get a 42, whatever I can write down. So how many such rows do we get? How many rows will we write down? 4 rows. If I had numbers which are n digits long, how many rows will I write? N rows I will write. Correct. And then what am I doing? I'm adding this. Then I'm adding this. I'm adding this. I'm adding this. So these two, when I want to add, yeah, I will take one step. Yeah. Then these n, I want to add these n digits now. Yeah. So I have some n digits. I will take some amount of time to add them. Then I will take some. So totally, is it clear that I have these n digits? I have to add these n digits. I have to add these n digits. Totally, how many such digits I need to add? I require to add. It is not n to the n. Is it n to the n?
Can I just say something, KV?
Yeah.
Yeah. So what Professor KV is saying as n to the n is n raised to n or n power n. Usually in school we say this way. So I just wanted to clarify that.
Okay.
Yeah.
No. So somebody wrote n to the n. It is not. It is. So let us do this a bit carefully. Actually, let us do this a bit carefully. Yeah. So if I have, say, 5 digits, and I want to multiply, so then I will write down first 5 digits when I multiply with this. Then I write down another 5 digits when I multiply with this. Then I write down a third 5 digits when I multiply, a fourth 5 digit when I multiply. And then I need to do an addition. I need to add these, then I need to add these, then I need to add these. And finally here, yeah, I need to add all of these. So there are these n bits, n digits I need to add, then these n digits, these n digits, and so on. If each of this, suppose these n digits, I take n steps. Suppose I take n steps for this, adding these n. Then n plus n plus n plus n, I will take about n squared steps. Is that correct? N raised to 2. Yes. So these are 2n minus 1. So I'm just calling it n. It's okay. So as you said, yes. So the number of steps, if each vertical steps, totally I'm doing so many additions. Is that correct? Find the final answer I will get in so many steps. 2n minus 1 times n. Because to add these n, I will maybe take n steps. To add these n, I will take another n steps. Totally, as somebody pointed out, I have 2n minus 1 steps. So in about n squared steps, I will to be very clear, correct, I may have to say 2n squared steps. Okay, why somebody asked me, sir, I didn't get. Can you read that question for me, Vinay?
Yeah, just give me a moment.
Yeah.
Too many messages. So, okay, I didn't get why it came to be n square.
Yes. Okay. Why did it come? Why did that happen? Because to add the first column, maybe I'll require just one step. But after a point, I'm saying in the worst case, I'm adding n numbers at every point. Yeah. Suppose those n numbers take me n steps. So the first column take me n steps. Second column, another n steps. Third column, another n steps. How many columns do we have? How many columns do we have? Whoever asked me the question, can you answer that? Around, actually slightly more than n. You have 2n minus 1 columns, as somebody actually correctly pointed out. It could be as large as that. Yeah. So there are, first column takes me n steps, second column another n steps, third column another n steps. The last column takes me another n steps. A total of 2n minus 1 columns, each take me n steps. So totally 2n minus 1 times n. For 5, so I will write 3, then I will write another 3. So if I want to multiply two 4-digit numbers, I will do this, then I will write this. I get 3 columns, correct? If I have 3-digit numbers, for the first I will write 3 digits, for the second I'll write another 3 digits, for the third I will write another 3 digits. But when I shift it, finally I will have 5 columns. Is it clear now? Yes, good, very good. Okay, so that is all I wanted to say. Okay, now we are here.
There is a question.
Then, yes.
Yeah. So the one question that came was, what about simple multiplication like 2 times 5 or 7 times 5? Would it also be
Tell me
done
how much.
as addition?
It can be done as addition also. It can be done as addition, or it can be done as multiplication. Even as multiplication, it's not too bad actually. Yeah, because if let me go back to the previous slide. Let me go back to the previous slide, wherever that was. After this, we started this. So let us look at this. To multiply two numbers which are as large as 10 to the n. 10 to the n means how many digits are there in the number? There are n digits in the number. Yeah. So I require around n squared additions, totally n squared operations, but assuming each operation I can do really fast. Yeah. And this is true on a modern machine. If I want to add numbers, I can do it really, really fast. Let us assume it only takes me 10 to the minus 10 seconds. So even if I give you 100-digit numbers, to multiply them, I'll require 100 into 100. This is rough. I'm not saying it is correct. I'll require so many seconds. But this is a really tiny number. Agreed?
Sir, my
And again,
question,
this works.
it was actually
Yeah.
slightly misunderstood. I wasn't asking about just the simple calculations. My question was, see, we know that each algorithm, one step is going to take approximately 2n square. I'm just going to ignore the minus n part. So it is taking 2n square per run of the calculation. But in that, aren't we just overlooking the part, let's say, in this 5127 into 4265? Aren't we overlooking the part where we are doing 7 into 5 is 35? So aren't we overlooking the complexity for that calculation? So that calculation 7
That
into 5 itself will
calculation
be
is very
6n.
easy. But that calculation, I claim I can do in about 10 to the minus 10 seconds.
Okay, so you're just adding that one clause there that you can.
Yes. So I'm saying very simple calculations like that, I can do really, really fast. I can do it in about 10 to the minus 10 seconds.
So but in the previous addition one, that was not the case. There we had to actually consider it in real time, where it was taking 6 and times
But
10 to
those
the
were
power
just
minus 10.
adding those are adding two n-digit numbers. These are all single digits I'm adding. In every column, I mean, I have one. I have just single digits which I'm adding, right? Because in every column, I had n single digit numbers that I'm adding.
So
Because
that will
every
still
column has
take
only numbers from 0 to 9.
that will still take 6 into 10 power minus 10 seconds, right? Like since it is a single
Yeah.
digit.
So no. So okay, you
So we're
can
just going
multiply
to
this whole
consider
thing by
it as
6.
this thing. We don't really bother since it's
Correct.
such a small this thing. Let's not go that detailed.
Exactly. I mean, yeah. I
Fair
that's why I
enough,
said
sir.
it is only approximate. I'm only being
Got it,
approximate.
sir.
Yeah.
Got
If
it.
you want to be very careful, you can be a bit more careful. There's nothing wrong.
Got it, sir.
Yeah. But all we are saying is, even these very large numbers, I can actually multiply really, really fast. Yeah. Is that clear now? Okay. So this is where we are. And now the question that I asked you, which I wanted to actually say, okay. So this was one of the questions. If I give you such a large number and I ask you to tell me if it is a prime, yeah, can you suggest a way to do it? Somebody says, yes, it is a prime. How do you know? This is actually hard. Well, we don't really know. Well, what is the best algorithm you can think about? How can you give me an algorithm which will do slightly this is a real, sorry. Yeah, if you give me can somebody suggest an algorithm for testing whether a number is a prime? What will you do?
You can check all the numbers till the root of that number and see if they divide that number. And then if one of them divides the number, then it is not prime.
Okay, so so what are you going to do? If you want to test, say, 987 is a prime, what are you going to do? Can you tell me? You're right. What you say is correct. I just wanted to repeat it. For this.
Basically, since it is 987 is just above 30 square, so you can maybe check till 31 for all
very
the.
Good. Yeah. Very good. So does everyone agree that that is reasonable? Yeah. So does everyone agree that if I give you a number, my God, what happened to this? Okay. Yeah. If I give you a number like this, 987, who was it? Anushka who said it? Somebody said it. I don't remember. Somebody said that you should do the following: check if 1 divides it, check if 2 divides it, check if 3 divides it, go all the way till 30, maybe 31 or 32 or something. Yeah. If one of them divides it, then you say, well, it is not a prime. Yeah. Very good. Now here,
can I just interrupt?
Yes, sure.
Yes. So as compared to the responses to the earlier questions, we have received few number of yes that they have understood.
Okay.
The why.
So let me come back.
If you can just elaborate.
Okay, sure. So what will I do? Okay, if we want to check if some number divides it. If some number divides it, then it is not a prime. Correct? Yes or no? We need to divide it only by primes, but we don't know what the primes are unless they give me a list of primes. That is the problem. So let us do it in this very simple way. I will say check. So the point is this: if no number from 1 to 32 divides it, yeah, I claim no number can divide it. Why is that? Because if you give me any other number, if you give me a number 33, say, divided by 987, what could be the other factor? The other factor can be at most 32. Yeah. When we check, so there I have given you 987. So I will check if 1 divides it. So what you say is right. So there are other numbers which divide it. I will check 1, 2. If I give you a, what is happening? This thing is really bothering me. 1 minute. I think somewhere we were here. Okay, so all this we did. We came here. Multiplication also is over. Now we are looking at primes. No, multiplication. This was, where are we? Okay. I have not. Okay. So this is where we were. Okay. Yes. So what we are saying is the following, that if I give you a number like this, yeah, if I give you a number as large as this, yeah, if a squared is bigger than this, yeah, then do the following. Check if 1 divides it, check if 2 divides it, check if 3 divides it, check all the way up to a minus, up to a. I claim if you give me a number like this, to decide whether it is prime, I will first try and see if 1 divides it, then I will see if 2 divides it, then I will see if 3 divides it, then see if 4 divides it. Up to a point where I come to a number a such that a squared is bigger than the number that you gave me. I claim if none of these numbers from 1 to a divided, then this number must be a prime. Because at least one of the factors, both factors cannot be bigger than a. Because if both the factors are bigger than a, then the number, when I multiply them, I'll get something which is bigger than the number that you gave. Okay, very good. Does everybody understand now? Again, if you give me a number and then I tell you, okay, there is this number a such that a times a is bigger than the number, I only need to check up till a whether one of them divides it, because there must be at least one factor which is less than that. Once again, I will tell you, okay, now did you follow? So if a squared is more than, if a squared is bigger than the number that you gave me, then I claim this and I check for 1, I check for 2, I check for 3, all the way here. This number, can both of its factors be bigger than a? Can both of its factors be bigger than a? No. Exactly. Both of its factors cannot be bigger than a, right? Because if I take two numbers which are bigger than a, then their product is of course bigger than a squared. So therefore, for me, it is enough to check if 1 divides it, check if 2 divides it, check if a divides. If none of them divide it, then we are done. This number must be a prime. Agreed? Whoever asked me saying, can you elaborate? Have you understood now? Yes, good. So therefore, we are doing this. But now the question is, how much time does it take? If I give you an n-digit number, how large is the number itself? Yes, exactly. Because then if I give you n digits, if I give you 4 digits, how large can this number be? It can be as large as 9999. Correct? If I give you 20 digits, the number can be as large as this, which is 10 to the 20 minus 1. The number is as large as this. Correct? 99999, but that number, the number itself is 10 to the 20 minus 1. But now you're telling me you have to check up to which is the number you're looking at. A squared is bigger than 10 to the 20. So A must be bigger than 10 to the 10. Agreed? Yes. So then we are saying the algorithm that you gave me said you check for 1, check for 2, check for 3, all the way up to 10 to the 10. Correct? You have to check if this divides, you have to check if this divides, you have to check if this divides, all the way up till here. Each of them might take 1 unit of time. Suppose it does, you can do it really, really fast. Yeah. If I give you a 20-digit number, and suppose you can check whether some small number divides this, suppose you can do that in 10 to the minus 10 seconds. Still, how many steps are you doing? How many steps are you doing? Yeah. So the number had 20 digits. So we had to say, we had to go up till 10 to the 10. Each of these took me 10 to the minus 10 seconds perhaps. But how many steps are there? I have 10 to the 10 steps. So so each step takes me 10 to the minus 10 seconds. So, but there are 10 to the 10 steps. So every time I have to check up till this point, I have to check. So this itself will take me 10 to the minus 10 times 10 to the 10, which is 1 second. Okay, this is not too bad. This is not too bad, I agree. But if I give you a 100-digit number, then how many steps, how many seconds will it take? Can somebody tell me? Hundred digits, so the number can be as large as 10 to the 100. Okay, let me know. Your answer is wrong. Why? Because the number can be as large as this. Are you agreed? Have you agreed? Yes, so one of you have got the answers correct. The number can be as large as this. Is it correct? Yes. So then I have to check for 1, I have to check for 2, check for 3, all the way up to 10 to the 50. Yeah. I have to check if this divides, I have to check if this divides, I have to check if this divides, I have to check if 10 to the 50 divides. Even if each of these takes me only 10 to the minus 10 seconds, how much time will the total be? No, 10 to the minus 10 seconds for this, 10 to the another 10 to the minus 10 seconds, another 10 to the minus 10 seconds, up to 10 to the 50. So the number of steps it will take me is 10 to the minus 10 seconds into 10 to the 50 seconds, which is 10 to the 40 seconds. Correct? 10 to the 40 seconds is a really large number. And as I said here, by the time the universe will come to an end. Because we estimate that the universe will be there maybe for 10 to the 30 years. Okay, so we were only dealing with 100-digit numbers, and it is taking us so long. Whereas for adding two 10-digit, 100-digit numbers, or adding two, multiplying 200-digit numbers, we did it really, really fast. Agreed? Yeah. So there is a problem. And this was the remarkable thing that so people were therefore looking for a better algorithm to solve it. Yeah. And it turns out that 3 Indian computer scientists actually solved this. They gave a very nice algorithm, yeah, which actually solves this. So Agarwal, Manindra Agarwal, Neeraj Kayal, and Nitin Saxena, they gave an algorithm. Oh, sorry. They gave an algorithm which takes only 10 to the 5 steps. 10 for a 100-digit number. 100-digit number, it only took 100 to the 5 steps, as opposed to 10 to the 50 steps. This is what our simple algorithm did. They gave a very interesting algorithm. Well, here I'm a bit loose. Maybe you should say 10 to the 8 steps. It doesn't matter. Something, it's a very small number actually. Yeah. Okay. 100 to the 8 steps we can deal with. Yeah, because it is 10 to the 16 times 10 to the minus 10, 10 to the 6 seconds. It seems like a long thing, but actually it is much faster than that. Yeah, their algorithm is much faster than that. Yeah, it certainly will not take this much long. So this is what was the great work of Agarwal, Kayal, and Saxena. They said to do n-digit numbers to check if an n-digit number is prime, they could actually do it in n to the 5 steps. And after that, people have worked better and better, and now there are better algorithms. So this is what I would call an efficient algorithm. Does that make sense? Yeah. Yes. Very good. So that is exactly what we want. What I wanted to convey to you, that there are problems that are hard, that seem hard to solve. There are many such problems. And if you look at integer factorization, the problem that I gave you, I will probably just write down this. So what is integer factorization? If I give you this number, if I tell you how to multiply, you know how to do it. But if I tell you what are the factors of this, we don't know. Yeah, it is not easy. If I give you an n-digit number, in this case, I think this was a 20-digit number, to tell me what the factors of these two are, we really don't have a good efficient way of doing it still. So therefore, that number that I gave you in the title, yeah, I don't know a good efficient way of checking whether the number is factorized. Yeah. So what is known is the following. What is known is the following. The computational problem is the input is x. Yes. Output you want y and z, so that x is equal to y times z. So this is the computational problem that we are looking at. Yeah, it is the same in the same format that we defined what computational problems are. It turns out the best we know takes so many steps for an n-digit number. An n-digit number can be as large as this. If I give you n equal to 150, I give you a 150-digit number. Then we know how to factorize it in n to the 150 cube. It's not too bad. N to the 1 by 2 to the, what is the cube root of 150? What is the cube root of 150? About 6, say 6. We know how to do it in 2 to the 6 steps. This is not too bad. Yeah, 5.31. Okay. Yeah. But now if I give you a say 1,000-digit number, yeah, then this is going to take even longer. Yeah. So factorization, we know of algorithms which work like this. Yeah. Yeah, 10 to the 1024 steps. Yes. So if I give you large numbers, we really don't know how to factorize them. Yeah, we don't know good ways of factorizing them. Yeah. But if you have a quantum computer, you can factorize it well, factorize it fast. And that is one reason why people are interested in quantum computers. Yeah. So I will end with just one slide, which is why is it people are interested in knowing that factorization is not easy. It turns out a lot of things that we do on internet, transactions on Amazon, you go and buy something, you pay, you get money. So all these transactions are based on the fact, the security of those transactions are based on the fact that integer factorization is not easy. We believe that integer factorization is not easy, and therefore we feel that when I'm doing all these transactions on the internet, buying goods of Amazon, ordering on Swiggy, all those things, we can actually do it feeling safe, because the algorithms that are used to do that kind of transaction, financial transactions, they are based on certain kinds of integer factorization. Yeah. So this is what I wanted to convey to you. Any other questions you all have? I hope it was understandable.
Yeah, so if you have any questions regarding this or related to this, you can just do a raise hand and we can take a few questions. And
yeah, we've
before
already
we
gone well past
conclude,
time. Sorry.
No, that's all right. So that's all right. Yes, Mayuk.
Yeah, ask me or ask me.
Sir, I didn't get how do you get that 10 to the power of minus 10 is the time required for doing multiplication problems.
Not
Like you
multiplication.
said.
So for simple additions or simple,
Yes, that square one.
For very simple operations on the computer, you can do it really fast. If I give you two single-digit numbers and I ask you to add them, or I give you two single-digit numbers and I ask you to multiply them, on a machine, even your laptop, even on your phone for that matter, the answer comes really, really fast. It doesn't take more than that much time. On a good machine, on your phone, it might take longer. Yeah, but on a good machine, on a laptop or something, it will take about 10 to the minus 10 seconds. Yeah,
Okay,
these are really
thank
fast operations. Yeah.
Okay. Thank you.
Yeah. Somebody else has a question? Yeah, please unmute yourself.
Hello.
Yes.
I remember that part in which you said you were talking about the biological computer, like you had a slide with the fetuses and everything.
Yes.
That's it. Yes. Well, I'm interested in biology. I'm always looking for ways to relate biology and math, which there are already so many relationships, like for example Fibonacci spirals and Nautilus shells and that sort of thing. Anyways, I mainly study invertebrates. Invertebrates like spiders and that.
That's fine. Yes. Okay. Yes.
And
actually, now that you say shells, if you look at shells also, you see the patterns that you see on shells, the very complicated patterns that you see on shells. Actually, those also are really patterns that can be generated. There is also some computation that is going on to produce those patterns. Yeah, and those computations are very easy to write.
Yes, so we could just stay over here talking about what computers, computing nature does all day long over here, because there are so many examples. But I'll just get to the point right here. So I anyways study invertebrates, as I said, very discriminated sorts of insects like beetles and arachnids like spiders. Anyways, what is interesting is that there is a specific family of spiders called jumping spiders, and they're like one of the smartest spiders that you will ever have seen. So if you with me and you were like having a jumping spider, so I have built this specific apparatus for studying their jumps, and what I have found is that they require they calculate the distance of the jump. For example, there are so many cases in which I've just put the platform too far away, so the jumping spider just refuses to jump and instead jumps on my hand or someplace else. Anyways, what I'm saying is that some spiders require computation to do their daily jobs, like the jumping spider. They're not entirely entirely as brainless as we thought them to be. And
Yes,
also,
of course not. Yeah, I agree. Completely agree. That ants, yes.
There's also there's also the topic
how
of
they
ants.
communicate, how they, bees, ants, they're all calculating things.
Wasps.
Even bees, wasps, when they are moving, bees also communicate.
Well, bees, ants, and wasps. Sir. Bees and wasps look a bit similar, but bees, ants, and wasps are all related. So there could also be a genetic factor in why they are living in colonies or eusocial, as some scientists would call them.
Yeah, correct. No. So you're right about what you said. That there are calculations that a lot of creatures are doing all the time. Yes, and they are as intelligent. I mean, do you think ants cannot discover primes? I am sure they can discover primes.
They're already discovering primes.
They have enough neurons in their body to discover that, actually.
Just precisely.
Yeah.
Thank you. Thank you.
Yeah.
Madhuvanti, you had a question?
Sir, yes, sir. Why only quantum computers can solve your algorithm?
No, that's a very complicated answer. There is an algorithm. If a quantum computer is built, and if you give me a number which is, say, 200 digits, then I can actually, if there is an algorithm which was discovered by this very famous mathematician now called Peter Shor, who actually showed that you can actually factorize it. If you give me 200 digits, it will take you about 200 cube steps. 200 cube is a very small number. It is only 8 into 10 to the 6. Yeah. So the algorithm uses the fact that so quantum computing, we actually, there is some way of computing with those inputs. So the inputs have to be given in a particular form, but those are not difficult to prepare. Actually, they're very easy to prepare those inputs. You can prepare the inputs in a certain way so that in the end, quantum computing is by that in the end, you can be guaranteed that you will be able to factorize them fast. Yeah, but it is using the power of quantum computing, because the way computation is defined in a quantum computer. A quantum computer does calculations in a particular way, not like what a Turing machine does. Yeah, but whether we can build quantum computers, we don't know. That is still a question mark. Yeah, some other question?
Can I ask my question, sir?
Yeah, sure. So, sorry, Madhuvanti, was your answer? Was my answer clear to you?
Yes, she said yes.
Yeah. Okay, good. Anything else? Yeah, somebody, sorry, you wanted to ask me a question. I interrupted you.
Yes, sir. So I had a question, like you said that you have written in the PPT, if someone discovers an efficient algorithm for factorization, it will disrupt the world of finance and security. I didn't
Yes, it will completely
how
disrupt.
will that happen?
That is because as I said, when I am buying something on Swiggy or I'm buying something on Amazon, you see, and I'm ordering this, after all, I put my credit card number, whatever, I'm putting various numbers. If your father, at home also, do you all buy things on the internet once in a while? Do you buy things on the internet? Do you do bank transactions on the internet? Do you know anybody in your home who does bank transactions on the internet? Do you know?
Yes, sir.
Yes. So who does it at home?
Mom, dad, both of them. Yeah.
Both of them do it. Yes. So what are they doing when they are doing some transaction? They have to give either their number on their debit card or their credit card, something they must be having. Yeah, or they must declare their bank account number, something they must be doing, so that the money goes from wherever, from either the credit card or the debit card, or from the bank the money goes to either, if you're buying it on Amazon, then or Big Bazaar, whatever, whichever is your favorite shop. Money has to go. After all, you purchase something, so money has to go. But that money is being transferred really across the net in some ways. Yeah. But
Yes.
to do that transaction, there is a certain sequence of instructions that are being executed actually. Those sequence of instructions that are being executed are based on certain kinds of sort of large numbers, actually two fairly large numbers that you actually take. There is some kind of a way of actually encoding those instructions. And it is assumed that while I can multiply those two numbers, if I give you the answer to after I multiply them, it is very hard to figure out what those two numbers are, which give you this. Yeah, it is based on that. Those instructions that are being executed for transferring money or whatever, they are based on the fact that there are two large numbers that are being multiplied. The answer, whoever, the bank knows what the answer is. The bank is using that big number for secretly transferring either money from your account or your details of your account, your passwords, and so on. The bank is using all that big number to do some calculations. If somebody is trying to listen on the net and sees what is the bank doing, he knows this large number the bank is using. He or she knows that the bank is using this large number to do the transactions. But unless he knows the factors of those numbers, he cannot figure out what your account number name is or the password to your account name is, and so on. But if somebody were to give you a fast algorithm to factorize, then this person who is the thief can give this large number and ask that person, give me the factors of those numbers. Then he will know your password, he will know your account number, everything he will know.
Okay, sir. Got it. Thank you.
Yeah, that's what happens. Yeah. Any other question?
Sir?
Yes, couple of them. Yeah.
Yeah. Yeah.
Is algorithm used in financial positions, sir, in like a field of accounts?
Those in the field account, look, what is when you want to do transactions on the internet, yes, those times you use some fairly sophisticated algorithms. Yeah, but if you're maintaining your records on books and so on, then you don't require it. But these sophisticated algorithms are used for financial transactions, yes.
Sir?
Yes.
Sir, earlier you mentioned that quantum computers will make it easier to factorize the integers. So could you please just brief? I know it will be quite long, but could you just provide a summary on how it does that and why it's faster than regular computers?
That is a bit difficult to explain unless I explain to you how computing actually happens on a quantum computer. And it is not the usual computing that we have seen. It is not the way you add numbers and so on. In quantum computing, what you do is what is stored inside the memory is not exactly what you see. It could be one of many possible things. Yeah. And when you actually measure, you know what is actually stored. One of them gets stored. Yeah. So the instructions that you use for a quantum computing or what exactly is stored in memory, it all it is not fixed in some sense. It all depends upon quantum mechanics. It is based on the principles of quantum mechanics. What you actually see is there is no, I mean, on a normal machine, if I ask it to store 5, it will store 5 exactly as 5. On a quantum computer, it will store 5 as a superposition of many things, unless I tell it, look, I don't want it to superpose, I only wanted to store the 5. Yeah? But then it gives you no advantage. Yeah. But if I store things in what is called a superposition of states, then I can manipulate with those superpositions of states using some very interesting operations. And those interesting operations allow me in the end to even do some nice factorization of numbers. Yeah.
All right.
That is a bit difficult to explain. Yeah.
All right, sir. I understand. Thank you.
Yeah.
Sir, actually, in
Yeah.
regards to when you were discussing about the biological aspect of algorithmic processes, you were talking about how DNA is actually, in a way, it's an algorithm which is basically it's being like a pack. It's unpackages
Absolutely.
itself and it makes it's a root set of code to create organisms basically.
Create
So
cells. Yes,
yeah,
absolutely.
that
Yeah.
is that if I may make an analogy here, that sounds very much like almost like the OS of a system, like almost like a booting code or something. Like it
It
creates
is.
all the
It is.
thing.
Correct.
But
No, it
sir,
is. Absolutely.
along with it, I wanted to discuss about the the fact like where like how our brains when we are born, even when after we are born, they are not as advanced as like when over time when you grow up through your childhood and by the time you reach adolescence,
Correct.
your brain is significantly more advanced than on the day one when you were born, and that is
Yes,
because
correct.
it is taking up millions of inputs, like from the act of walking where it has to like start learning how to balance and all. If I'm just going to use the term machine learning here because I don't know how to explain it briefly in this question. So it's almost like a machine learning algorithm where your brain is slowly learning how to balance itself, taking the inputs and accordingly moving your motor this thing to function as it is. So my question is like, are those are kind of like those are basically like evolving algorithms, right? They are like over time slowly as time changes, as it's what we call experience, double quotes what I'm going to use because I have lack of better term. So it's kind of like over the experience the algorithm is
You
able
learn.
to
Becomes better and better. Correct.
it is, yeah, it
Correct.
is basically what we call evolution or adaptation in short. Adaptation is
Correct.
in that one point and
Correct.
evolution is over a
Correct.
long period of time. But sir, I wanted to know more about the underlying difference between both these things. Like I can understand that the difference is basically this one is an algorithm which is changing over time and it is being created in your brain, and your brain is simulating more closer to the transistor model of algorithms what we are going with gates and logic to run an algorithm. Like we have a transistor, I believe the IBM used to use semiconductor wells, right? Like they will just have a well which will
Yes.
hold it. And in our brain, we use sodium pumps, I'm guessing, yeah, which just like it spits out that much charge, electric charge. So it is, our brain is very similar to that. If that is analogous, then what is the DNA's method of algorithm
No, but you
similar
have to
to?
produce cells. No, you have to. No.
So
DNA
it
is
is producing a
primarily.
cell, but then how are those chemicals? Also, I am very interested in the fact that the DNA is able to use 4 base units instead of like how we use two
Yes.
in a binary. It is able
Yes.
to use base units consistently. It is able to use 4 base units which do not mess up. They are able to stay up. Like they are not able
They mess up once in a while.
consistently.
They mess up
We
once
call
in a
that
while. I mean,
mutation.
most often they are fine. But for some people, no. I mean, you have probably seen some individuals who are who have some mild deformations and so on. So their DNA is really messed up. So
But
that's
that
okay.
happens even in your computers, right? In computers,
Correct.
I'm not talking
Yeah,
about
but that is
glitches, like mechanical glitches. I'm talking about bit upsets or like bit flipping, SEUs and those kinds of events where, like, due to a cosmic ray, the well is getting decharged and it flips the bit. So like
correct.
it sounds very much like a mutation, like how mutations are happening in humans, or to which can lead to either different evolution or it can even lead to cancers. The similar way we are having bit flips in the computer, which is either leading to glitches or it can even completely destroy the computer. It gives you the blue screen. So my thing is like, but then what is this DNA? It almost feels like a ternary machine, but it's a ternary machine. Sorry, not ternary, quaternary machine, which is only allowed to but it is like limited. It cannot do whatever it wants. It has to stick to this thing. So I was just confused, like, what does this how does this
So
work? And
so when you're born, those instructions are there. They're part of your genetic code. Yeah, that's what happens. Yeah, so your genetic when an organism is created, the genetic code is present in the DNA, and those instructions are there for your life. Now, in the brain, there is something different which is happening. Namely, the wiring of the neurons is something that is very elastic. That actually can rewire itself. But that itself is some kind of, as you said rightly, that is a learning that is happening. But nevertheless, if something gets damaged at a later point, yeah, even in your brain, there is enough ways to actually train it to regenerate those things also. But at those points, perhaps there are instructions with your DNA and so on. Those probably kick into. So while what is present in your standard DNA are instructions which in some sense the cell has to follow all through its life. Yeah, and it
sir,
follows it for most part of the life.
that's what,
At
yeah,
the
that
end
is
of the
what
life, there is
old age is basically, that not able to follow it for
yeah,
any
exactly,
longer.
yeah,
So sir, is it
exactly.
even feasible?
That's what happens. Yeah.
Is it even feasible? Is it like, am I going? Is it completely a stupid idea, or is it even feasible to, let's say, mimic that kind of DNA style of computing? You know, the DNA style of computing happens to be like it
No. So
is.
there are there were in the early 90s people tried to build DNA computers also. People
So
have
the
built it also.
the way it is,
They,
like, you have four separate units instead of a binary where you have only two fundamental units. You're having four separate units by four chemicals instead of electron charges or deficiencies. So imagine, like, you can say, and the thing is, since DNA by nature is very, it is a coded thing, and it is very limited in terms of functionality. If you make one DNA, it has to be for something. You cannot just it cannot like change over time. So imagine for your factorization problem, let's say there is a DNA computer which is having four base units, and that can, even though that is only able to solve the factorization, this thing, it is almost like a modes of computing, no, where you have the fast mode and the slow mode, almost like how modern day graphic computers, they change their calculation, the ray calculations and all, they change the mode of ray calculations depending on the usage. So is it even feasible to think in such a way, or is it like, is there a fundamental law or something which completely blocks down or makes this prone to fail?
No, prone to what? Prone what? I still didn't get. What is your actual question?
Sorry, Hitesh, we are actually running out of time. If it's a question that is going to take some more time to discuss, can we do it at some other time?
I'll wrap up. It's okay. We'll have it some other time. Thank you for your time, sir. Anyways.
Thank you, Hitesh.
Yeah.
Madhuvanti, you have a quick question. If it is quick, you can just ask.
Sir, you were talking about quantum finance and finances. So, is there any relation between quantum physics and quantum finance or computing?
Quantum computing, yes, it's based on the principles of quantum physics. Yes, it is. Quantum computing is entirely based on the principles of quantum computing. Yeah,
Okay.
We expect, but whether we can build it, we don't really know. But they have built some small quantum machines, but not big quantum machines yet.
Okay. Okay. So yes, I think we'll take a pause. Before you all leave, if you can just stay back for maybe another 3 minutes, we'll quickly share 3 videos, which can be very useful and interesting to you about a couple of programs. But before that, let me just take a moment to thank Professor KV for taking out his valuable time and making this so simple for all school students. I really didn't think that it can be so brought down, and the way you built up all the ideas about computation, about how many steps, about how much time will it take. I think that was really wonderful, Professor KV.
Thank you.
So
Yeah. Thanks.